This is a setup from our previous video. We're using Raspberry Pico to control motor and servo. Currently, code flips motor direction and orientation of the servo every 5 seconds. And in this video, we're going to add a Bluetooth. This way, we'll be able to control both direction and speed of the motor and orientation of the servo. Here is how everything is connected. Power comes from a dedicated USB adapter and not from your computer. Power goes to Pico to VC's input, and in addition, we split power to servo, and Pico provides the control signal from GPIO 16. Since we cannot use motor directly, we use DRV8833. And we run a FreeRTOS on Pico itself. Pico uses FreeRTOS to manage independent tasks. And in our case, we need two of them, one to manage Bluetooth and one to control our servo and our motor. When data is received by Bluetooth, it needs to be passed to the control task, and we're going to use a queue for this. Our queue has a specific properties. It has size 1 and it being overwritten with the newest data for the control task. Our protocol is very trivial. We use just 3 bytes, one for motor, one for servo, and one just in case. Values for motor and servo are in the range 0 to 200. For example, for motor, our 100 is stop, 0 full reverse, and 200 is full forward. And servo looks the same way. This is our code base from the previous video. We are going to tell Codex what exactly we need. We basically repeat our protocol, 3 bytes, the values, and so on. And also we instruct not to make any other changes to the code base outside of what we ask. Let Codex to do its magic, and now we can do a quick code review. We can see what was changed and what was added. In this particular case, we can see the default values are actually pretty good, and the name of our device became Pico Car. Nice touch. This is our new file, and we can see how the controls actually works. We can see the main loop and the task which has been triggered every time a new command is being received from Bluetooth via the queue. To flash our code to Pico, we need to connect Pico to our computer. And as usual, we need to disconnect every motor and every other device from the Pico. The easiest way to do it is to disconnect power lines from the Pico itself. This way, only signal wires are connected, but no signals will go through, since ground is not common anymore. After flashing the device, we can see in the serial output how the device behaves. And we can see that control values are hundreds, which implies motor will be stopped and servo will be in its middle position. Here I'm connecting multimeter. This way I can test the device while it's still connected to my USB on my computer. I connect black to the ground, and I use red to touch the power pin to make sure ground is actually ground. Otherwise, I could by accident send 5 volts into the Pico input, which would destroy the Pico. GPIO 13 is always high, and we're going to leave multimeter connected to GPIO 14. I'm using an RF application, which is available both on iOS and Android. This application allows sending raw data into any Bluetooth-enabled device. So we're going to connect our car to Pico and send our magical 3 bytes. The default value was 100 for both servo and the motor. So now if we're going to send all zeros, this will imply the motor needs to go backwards. And we see PID goes high, which implies motor starts working. I have disconnected Pico from the computer and provided power from my USB adapter. Now we can try manage both motor and servo using Bluetooth. I'm sending various inputs to Pico to see how both servo and motor behave. Input is expected to be in hex, which implies 100 is 64, 200 is C8 and 0 is 0. Looks like Servo works as expected, and the motor changes direction as well. And here is the problem. When I try to run motor half speed, I send the data, but the motor actually does not move. Let us Codex what actually is going on. Codex found a problem, which is basically not enough torque to start the motor, and Codex suggested the code for us to handle that use case. After flashing the device and reconnected power back to make sure we're not using USB on our computer, we can run a few tests. Our 00 test is supposed to be working just alright. Our full stop works as well. Our half speed for the motor looks like it's moving now. We can test quarter speed as well. Our Bluetooth is up and running, everything looks alright. And before concluding this video, we would like to add some failsafe, because this code is about to be used in the NRC car. We want to implement a failsafe. When Bluetooth is disconnected, we would like the motor to stop. A quick code review. We can see that timeout was added into reading the queue, and in case that is happening, the reset motor function being called, which will reset the motor to stop. Code looks good. We are going to upload it to the device and commit code to the Git repo. In the next video, we're going to build a React.js application. We are going to run it in the Chrome browser and use Bluetooth to control Pico.